Continuing part A of section 3.4, I just want to do a couple more challenging examples. So this is still section 3.4 part A, but with some more challenging examples. So let's see. So always start with looking at the domain so you don't forget. Like we saw in the other example when we got, I want to remind you what happened here. It looked like there was no restriction, but I had to look back at the previous functions to find out 0 never would have been a possibility. So make sure you start with your domain so you don't end up forgetting a restriction that should have been there. So f plus g, I'm sorry, starting with f. So my domain, actually this one doesn't have any domain restrictions, so this is all real numbers anyway, except for when we get to the quotient, because then we have to say, okay, well, g of x cannot equal 0, so that means x squared minus 4 cannot equal 0, so that means x cannot equal positive or negative 2. All right, so we do have a restriction on the domain of the quotient, but the other three do not have a restriction. All right, so finding the sum. So f plus g, remember that's just an abbreviation for f of x plus g of x. And I have 2x squared minus x plus x squared minus 4. And combining like terms, I get 3x squared minus x minus 4. And as suspected, the domain here is no restrictions, so that's negative infinity to infinity in interval notation. All right, moving on to subtraction. So a similar process, except this time it becomes crucial to have your parentheses around the second function so I don't forget to distribute the negative to each piece, so distributing that. So I get, before I combine like terms, I have to distribute. So I get minus x squared plus 4. And now I can combine like terms. 2x squared minus x squared gives me x squared minus x plus 4. And that is my final difference. And the domain, as expected, is no restrictions. So that's all real numbers, or that in domain interval notation. Now for the product, I gotta have to FOIL this one. I did forget to write f of x times g of x. All right, so foiling this, I get, let's see, 2x to the 4th minus 8x squared minus x cubed plus 4x. Combining, nope, no like terms. So I'm going to reorder this just to have it in standard form and have the exponents decreasing in order. So I'm just going to reorder it like that. And that is my final product. Can't reduce that. So, and the domain, as expected, no restrictions, so negative infinity to infinity, or all real numbers. And then making space for our final operation of the quotient. Remember, our domain for this one is a little more restrictive because I got to leave out that plus or minus 2. So that one should go from negative infinity to 2. Oh, it's plus and minus, I'm sorry. So it's actually going to be a 3-part domain. So the domain for the quotient is going to be negative infinity up to negative 2 union. I'm going to need a little more space still. Negative infinity up to negative 2, and then not including negative 2 to positive 2, and then also not including positive 2. So this is the way to write this restriction in domain notation. So you can see why sometimes it's more convenient to write your notation like that. But our textbook tends to use the interval notation, especially on our tests. So both of those are correct. This is the one that we're going to use in this class, though. Okay, so now finding that quotient. So f divided by g is, so that's f of x divided by g of x. So that's 2x squared minus x over x squared minus 4. And again, it's tempting to cross off those x squareds, but you can't do that because it's not in every term. It's not in the x or the 4, so can't restrict this. Cannot reduce this at all. I'm just thinking you could actually factor the denominator because that's a difference of squares. If I were to factor this, then I would get in the denominator x minus 2, x plus 2. And in the numerator, I could take out a 2x and be left with x minus 1. So still no common factors, so there's really no point in reducing it. So either of these answers would be correct, factored or unfactored. And my domain restriction is excluding both those 2's, which you can see in that factored form that you wouldn't want x to be equal to 2 or negative 2. All right, so I'm just going to make sure that this is clear that this domain is strictly for the quotient, and the other 4 is all real numbers. Other 3 are all real numbers. All right, one more challenging example, and then we'll move on to the next section. Start by finding the domains of the original functions. So with f of x, that's under a square root, so that tells me that this minus 2x, 1 minus 2x, it must be greater than or equal to 0, which leads me to the domain of, let's see, I'm going to have to do that off to the side here. So 1 minus 2x greater than or equal to 0 gives me negative 2x greater than or equal to negative 1, and then divided by negative 2, negative 2. So I'm going to do x, flip the sign, and that's 1/2. So x is less than or equal to 1/2. So my domain here is going to be x is less than or equal to, what was it? 1/2. So I used this little side note to find that domain for f. I'm going to erase it from here to keep it a little cleaner up here and just keep the domain, which was x is less than or equal to 1/2. And we can put that in interval notation at the end. All right, and then the restriction on g of x is that x is in the denominator, so x cannot be equal to 0. So when I take the intersection of these two domains, then I have to leave out the 0 as well. Well, I guess 0 is already less than 1/2, so 0 has already been left out by f. So that doesn't change our domain. Wait, yes it does. I'm sorry. I was thinking about 0 is less than 1/2. Sorry. So, okay. So I'm going to go back over here to when we look at the domain of f intersection the domain of g. So before I even get into these functions, the challenging part of this one is the finding those domains. So the domain of f and the intersection the domain of g, which is x can't be equal to 0, so that lists, so I like to kind of think about it on a number line. We said x cannot be equal to 0, so there's an open point at 0, but also x has to be less than 1/2, so 1/2 could be here. And then it's less than that, follow that arrow. It's less than or equal, so it's going to have a closed circle there, but it has to have a hole at 0. So intersection means both those things have to be true. It is is less than or equal to 1/2, and it's not equal to 0. So to write that in interval notation, I have to start at negative infinity, go all the way up to 0, leave out the 0, and then continue on to 1/2 and include 1/2. So that should be my domain restriction for the first 3 operations. So for these 3, when I intersect the domain of f and g, I get this, negative infinity to 0, and 0 to 1/2. Whoops, sorry. Including 1/2. And when I look at the additional restriction of g of x cannot equal 0, well, there's no way for this to equal 0 since 1 over any non-zero number is not 0. So that restriction is not necessary. It's already excluded. It's already excluded there. Actually, it's not excluded. There's no restriction on that. There's no way to make g of x equal to 0. So there, we'll have that same domain for all 4 operations. Okay, so now we have that domain for all 4 operations. And then let's do the operations. So f plus g, that is radical 1 minus 2x plus 1 over x. I really can't combine those, so that's my final sum. And my difference, again, I won't be able to combine these. These are very similar, except changing that plus to a minus. And then multiplication, I can't do much with this, except I could treat that like it's over 1 and say, just express it as a single fraction. And then the quotient, so I have f of x, and then I'm going to do this kind of division, divided by 1 over x, which is the same as 1 minus 2x. Flip the second and multiply, which means I can get rid of that 1 in the denominator, and I get x out in front, and I get 1 minus 2x in the square root. So that's my final quotient. And again, all 4 of these will have that common domain of this thing right here.